So welcome to our August 25th virtual star party, and thank you all for coming this evening. We're all very excited to be here. It looks like that a lot of us will at least have some clear skies, at least momentarily. So we're hoping that that's going to continue, and folks that are a little hazy right now, hopefully their skies will clear up pretty soon as well. So I'm Dr. Billy Teets, and I am the astronomer and the acting director for the Vanderbilt Dyer Observatory. With us tonight, we have a whole bunch of other people. So with me from the observatory is Alex Rockefeller. She's kind of like part of the glue that holds this observatory together. She does a little bit of everything. She's our administrative assistant. She's our social media guru. So she's going to be helping us tonight with questions. We also have Helen Morissette, who's our events coordinator. So she's also going to be helping us tonight with their questions and any issues that come up. So we're hoping to do these on a monthly basis, and each time that we have new things going on, new people joining us, we'll be sure to post updates on our website. Here you can see Vanderbilt Dyer Observatory here in Brentwood, Tennessee. So we are currently closed to in-person visits, but do check back to our website for updates on any virtual events that we're going to be doing in the near future, and any updates on when we might be reopening to having visitors up here. So we're going to get started by tell you a little bit about what we're going to do tonight. So I'm going to start off the show with a little bit about the moon, specifically one or two features on the moon. And then we're going to go over to some other folks, including Adam Fens, who's at the Bays Mountain Park and Planetarium. We're also going to go out to the western part of Tennessee to Jerry Feldman, who's with the Memphis Astronomical Society. And then we're going to go all the way up into Canada and join Nick Vieira at McGill University. And then we'll come back, visit with Theo Wellington, who's with the Barnard Seaford Astronomical Society. I'll come back to me, and then we will end our presentation part with John Kramer, who is also part of the Barnard Seaford Astronomical Society. So we've got a lot going on. If it clouds up, we're still going to have a great time. So please be sure to enter some questions into the live chat. And at the end of each little segment, we will try to address a few of those questions. And then at the end, we'll do a final question roundup. So we'll try to get to as many questions tonight as we can. Okay? All right, so the first stop on our tour tonight is what we call the moon. And we are going to be first looking at a feature. It's kind of a fleeting feature. It's known as the lunar X. So this is a really nice simulation that is showing a first quarter moon. It's actually representing our moon right now. And if you look very carefully along this day-night edge, you're going to see a lot of details. And if you look very carefully, you've got a keen eye, you'll be able to pick out what we call the lunar X. And so the lunar X is actually formed by three craters that just happen to form right next to one another. They're basically butted up right next to one another. And so their edges, the rims of the craters stick up. And these craters are a couple of miles deep. You can see some of the stats of those craters over here, and I'll show you those in just a moment. But when those crater rims kind of butt up next to one another, the rims, the tops of the craters, catch the sunlight before the bottom parts of the craters. And so the outline and sunlight of those crater rims creates this feature called the lunar X. So hopefully you found it. If not, here we go. It's right in that little box there, okay? And before I zoom in on it, I'm actually going to switch over and go live to our main telescope here at the Dyer Observatory, the Seaford Telescope. And this is a view of it right now, or view from it right now. And you can see how the image is kind of waving a little bit. And so that image waviness, in fact, I'm going to move the telescope just a little bit and recenter the lunar X. So lunar X is right in the very center. But that waviness that we're seeing is due to our atmosphere. So if we were out in outer space and we were using this telescope or any other telescope to observe the moon, that moon would look absolutely still. Okay, and so thankfully clouds have cleared out enough for us tonight, and the atmosphere is not too terribly turbulent. that's a mouthful, that we're able to make out the lunar X pretty well. So the three craters that make up this feature here, here's our X here, the three craters right here, and then the third one is right over here. Okay, so we don't necessarily have to have a fourth one down here, and there really isn't one. There's kind of a flat area, and if you look at this feature or this area in just a few hours, as a matter of fact, you'll be able to see some changes in this, which we'll investigate in just a moment. So the crater over here is called Purbach. This one's called Lakaya, and then this one is, I can never pronounce this correctly, Blanquinus. So a lot of these craters have names of famous astronomers or just people of notoriety in the past. In fact, we even have a crater on the moon named after Edward Emerson Barnard, who was the first, really one of Vanderbilt's first astronomers. And we even have a crater named after Carl Seifert, the first director of our observatory here. So I'm going to switch back to, well, actually, I'm just going to kind of move up just a little bit here. And you can see that there is a lot of detail in these images here. So if we look at this crater, for example, you'll notice that the bottom floor of the crater is becoming visible. You still see some shadows over here, but notice that those shadows aren't really smooth. You can actually make out that they're quite jagged, which, you know, we're viewing this crater from above, so it's very hard to actually figure out how essentially rough or jagged that crater rim is. But if you were standing on that crater rim, the sun would just be coming up above the horizon for you. And so the shadows that are cast, that really gives you an idea of just how rough that crater rim is, even though we can't really see it here from the Earth. And you can actually do some calculations if you wanted to, for those of you that love math. You can first determine the size of the crater, and then based on the size of these shadows, you can actually figure out how deep the crater is. It's a little bit of geometry and trigonometry. So if you're looking for something to do on a Friday night, try that out. It's a lot of fun. Also, in craters like this, we often see little mountains. And I say little, these can be several miles high. So they look very, very tiny from our view here on the Earth, but they are in fact pretty tall. I'm going to go up, actually, I'm going to switch back over to our, my slideshow right quick. I just want to point out a couple of other things. So here's another nice view of the lunar X. This time you'll notice that the image is flipped left and right. So one thing we had mentioned in our first star party was that telescopes will often flip an image left to right, upside down, or a combination of both. Okay, so if your image is backwards or upside down, that doesn't mean your telescope is broken. Okay, so this is more of a view as you would actually see it if you could, you know, say, if you could zoom in with your eyes on the moon. All right, let's go to another, or let me point this out. So here is the lunar X as we're simulating it pretty much right now. And I mentioned before that this feature is pretty fleeting. It doesn't stay around for very long. In fact, you can only see it for about 4 to 6 hours every month. Okay, so this is what it looks like right now. 4 hours from now, so if we go to about midnight, 1 a.m. in the morning, that same area will look just like this. So now you can still kind of make out that X, but it's not as easy to pick out now. Okay, and so just a little bit of change in the altitude of the sun on the moon is going to affect how we see things. There's one other feature I wanted to point out. I am also starting to run out of time here, so I'm not going to use the main telescope to look at it, but we'll zoom in on it here. There's another letter on the moon, and that's called the lunar V. It's not quite as elaborate as the feature that we just saw with the lunar X, but nevertheless, it is a pretty neat feature. This one's a little bit easier to pick out, and it's visible around the first quarter phase like we see here in this picture. But if you scan along that terminator, that day-night edge, you'll come to this little area here, and that's our lunar V. Okay, so I'm going to zoom in on that, give you an idea of what that looks like. So there it is right there. So this feature is really dominated by one particular crater. It's called Ukert crater. And there are a couple of other little craters around that help to kind of create this V formation. So this one you can typically see for a little bit longer than the lunar X. A couple of other things. So we mentioned before how some of we've got a first quarter phase here, and we can see some really nice features along this terminator. Notice how we get over to the right side of the moon here. You can see some craters, but notice that they don't stand out as nicely as we saw over here. So a lot of people think that the best time to view the moon is when it's full, because you can see the entire moon. That's actually the worst time to view it because you don't see the shadows. In fact, from the viewpoint that we have of the craters, they don't really have shadows, so it makes them very hard to point out on the surface. For instance, you can see how well this crater stands out, but how much harder it is to see like this little guy over here. Okay? In fact, we looked at these two craters in our first star party. Let's see, I think that is all that I had. So I think that we are going to go to just a couple of questions before we head over to our next presenter. So we got one question here. Why are there so many craters along this light dark edge? So that light dark edge is again what we call the terminator. And every night that appears to shift a little bit. There's actually, for example, about just as many craters here as we would see over here. So the first phase like the first quarter, we can really make out a lot of those craters because a lot of those craters are casting shadows. So if we were to go to full moon right now and look at this exact same area, you'd have a much harder time to be able to see any of those craters. You'd still be able to see them, but it would just be harder to make them out along the surface. It'd be harder to see some of the details in them. Another question, when is the best time to see the moon? So the best time to see the moon, if you want to view it through a telescope anyway, you want to get the moon at some point before it's full moon. Generally, if I were to look at the moon, I would say anywhere from about, say, 2 or 3 days after after new moon, when you first start to see that moon as a really thin sliver in the sky, you can start to really see some details in the craters up until maybe a week past that. Once you start getting around full moon, it gets harder and harder to see any of the craters along that terminator. So, and one final thing I'll point out before we switch over, notice that in some of these areas, like these dark gray areas, you really don't see craters. These are actually younger areas on the moon. And notice how they're kind of round. Well, these are actually large impacts. These happened several billion years ago, about 4 billion years ago, early on in the solar system's history. Large objects hit the moon, created these huge craters that then filled in with lava that then solidified. So that material has a little bit higher iron content, and that tends to make that material darker. Okay. Another question, I think this will probably be the last one before we, well, no, we may have time for one more question after this. What is my favorite crater? That's really hard to pick out. There are a couple of craters. I don't know if I can see them in this picture here or not. There are a few craters that it's like 4 different craters, and they make a spiral pattern. And as you go from one end of that spiral to the other, they actually get smaller. So it looks like somebody, took some time to actually make a very nice geometric pattern. It's really interesting looking. But unfortunately, I can't. Oh, actually, I can see them. Unfortunately, I can't zoom in right now, but they are right there. So right there's that spiral of craters. Okay. All righty. Well, hopefully you all got a nice view of the lunar X. And if you've got a small telescope at home, you don't need a big telescope like the one I'm using here. Just a very small telescope, even a pair of binoculars. Especially if you can hold those binoculars steady, that will give you a view of the lunar X. Now we saw it this month. It'll happen next month, but remember that timing is crucial. When the lunar X occurs next month for us here in Nashville, or really in North America, the moon will still be below the horizon. have risen quick enough for us to catch a glimpse of that. So we won't see it in September, but other folks, across the other parts of the globe will be able to see it. But come October, we'll have another chance to see it here. So if you miss it tonight, or if it's cloudy where you are, don't worry, it comes around once a month. So, and there are websites that will also tell you where to find it. Okay, so I think that I'm gonna stop my screen share here. I think we are now going to go over to Adam Than's over in the Bays Mountain Park and Planetarium. So Bays Mountain Park and Planetarium is in Kingsport, Tennessee, way over in the northeast corner of the state and tucked up next to Virginia, North Carolina, and Kentucky. So Adam's been into astronomy since he's 12 years old, and he's been at Bays Mountain since 1992, educating about and sharing the night sky. So I'm going to turn it over to Adam now for, hopefully we'll get a chance to take a look at Saturn.
Thank you, Billy. Hi, my name is Adam Than's. I'm the planetarium director at Bays Mountain Park and Planetarium in Kingsport, Tennessee. And I'm happy to be here and share the night sky with you, or at least try to share the night sky with you. That's kind of part of astronomy, is dealing with the weather. It's a common story that we all have to deal with. And so I'm going to show you what I am seeing through my camera right now. That is a live view, and you can see that you can just barely see stuff, but I do have pre-recorded content, so I'll be happy to share that. But right now my sky over here in East Tennessee is almost totally gone. So let me go to some other things to show you. Okay, so I took these images a while ago, and if you look carefully, you can see a lot more detail there. You're going to see the planet Saturn itself, and I really should introduce Saturn before I start talking about it. Saturn is a planet. It orbits the sun just like the Earth does. Saturn is farther out from the sun than we are, and so it goes around the sun a lot slower because of that far distance. Saturn is one of the gas giant planets. And in our solar system, the first 4 planets are called the terrestrial worlds. They're small, rocky worlds. If you were able to breathe the atmosphere and handle the pressure of the atmosphere, you could walk on their surface. Though Earth is the only place that we can just walk around, safely without a suit. But then after the 4 terrestrial worlds, we have the 2 gas giant planets, Jupiter and Saturn. We're going to see Jupiter later on tonight. Saturn is the other gas giant. Then after that, we have 2 more Jovian planets, just like Jupiter and Saturn, very big giant planets, but not as big as Jupiter and Saturn. They're called Uranus and Neptune. They are ice giant planets. So those planets are a fraction of these. And because they're so far away, their atmosphere is more slushy, like an icy or slurpy, than these planets, where their atmosphere is just gases from the top of the atmosphere, which is what we're seeing, all the way down to near the surface of what may be in the center of these planets. Saturn is about 850 times larger than the Earth, the planet itself. So you can see the ball there in the middle. That is the planet Saturn. It has a very thick atmosphere. You notice the tan colors. You'll also notice some features on the surface. So you're going to see on the planet some banding, some very slight banding. And what's happening is that actually both Jupiter and Saturn rotate very quickly. Jupiter is a little less than 10 hours. Saturn is just a touch over, I believe. And so because of that fast rotation, it is stretching out the bands of clouds, stretching out the clouds into bands. And if we were able to see like a really super duper view of Saturn or even Jupiter, you're going to see a lot of structure within the bands of clouds and color differences. That kind of whitish band that's close to the center That's actually ammonia. And then we have kind of a darker band as you go down. Then it's kind of a slightish kind of faded tan, like a mid dark tan. And if you look at the very bottom of the planet, you'll see what looks like a kind of a black circular area, and that's the polar region. It's the polar hood, and it's not reflecting much of the sun's light, and so it's actually dark looking, and you can see that. And that was taken with my telescope here. And just to let you know, I'm using a refractor telescope that has a lens in the front to gather the light. Look at the rings. And that's the part everybody loves seeing. The rings don't physically touch the planet. They're not attached to the planet. It's not like a big record sticking out from the planet itself. But the rings are actually made up of rock and ice. The rock, of course, does not reflect much sunlight at all, but the ice sure does. And so just like how when it snows and it's really bright out, all that light is reflecting of the sun is reflecting off of the snow, and it makes it very glary and very bright. It's because they're ice crystals and they're acting as little tiny micro mirrors. They're not actually white. Snow is not actually a white color, it's clear. So the rings of Saturn are kind of the same, and that's why we see them so well. There is the Cassini division. You see that little gap there. And we thought that there's nothing there. Guess what? There is. There's just not as much ice, but there is rock. And we actually sent one of our Voyager craft, the spacecraft back in the 70s and 80s, through that. And we were lucky that it didn't collide with something and destroy the craft. But interesting things. And through a basic telescope, and if the sky is steady and, of course, clear, like it's not here, you'll be able to see that gap in the rings. And so that's the Cassini division. There are some other features with very high resolution images that you can see. So what else can we see with Saturn? Well, if we actually want to overexpose the image, Saturn now looks like a little UFO. That's because this image was very overexposed so that we can see those little dots. And those little dots are some of the moons. There's actually more than 70. There's almost 80 moons around Saturn right now that we currently know of. When I started in school, it was 12 moons. And then we started discovering more and more. Now we're approaching 80. So they're just smaller and smaller moons. Well, look at the little dots. I've got them named of the ones that I could see. Some of them are very faint. Notice Titan here. That's actually the largest moon of Saturn. And it has actually been visited by a spacecraft. Now, we sent a spacecraft out to Saturn a while ago called I'm blanking on it already. Cassini spacecraft, and it had a probe called Huygens, and Huygens landed on Titan, and it went through a thick atmosphere of Titan. It's the only moon that we know of that has an actual atmosphere like that, and it went down to the surface and imaged it. So it was pretty amazing. Let me show you. This is a recording of Saturn through the telescope when the seeing was obviously, not cloudy. So this is an actual video recording. You can see the bands of clouds. You can see the Cassini division a little bit. A photograph tends to work better than video. But you can also see the image kind of wiggle around a little. That's the atmosphere of the Earth. And that's what I have for that. So let me go back to my main image here and see if there's any questions from anybody. I'm not able to do any other objects, unfortunately, but.
All right, we have a couple of questions here.
Yeah.
I watched the movie Ad Astra. Brad Pitt's character traveled through Neptune's ring perpendicularly in about 2 minutes. About how thick are the rings of the planets?
That is an excellent question. So how thick are the rings of the planets? Saturn's rings. Okay. Think of it this way. First, you saw the planet Saturn, as a disk, a ball, and it's 850 times larger than the Earth. The Earth is about 8,000 miles wide. The rings of Saturn are actually larger than Jupiter in diameter, much larger. They're about 250,000 miles wide, if I remember correctly, about the distance from the Earth to the Moon. Maybe a little less than that, but on that order. I hope I'm not saying really the wrong numbers. So I think I'm close. The thickness, though, about 300 feet. Let that sink in for a moment. 300 feet. Very, very thin. If you were a spacecraft and needed the speed to get out to a planet, just to escape Earth's gravity, you would need to be traveling at over 25,000 miles per hour. You would just zip right through those rings. It'd be an incredible sight to see, but it wouldn't take much time at all. The rings of the other planets and Jupiter, actually, and Saturn, I'm sorry, Jupiter, Saturn, Uranus, and Neptune all have ring systems. So does Pluto, a little bit of a ring system. But those four large planets, they're not even as plentiful as Saturn's rings. So they're going to be less dense and probably just as thin. That was a great question. Any others?
Yes, and speaking of Saturn's rings, is Saturn losing its rings?
Ooh, excellent question. And the answer is no. And there's a reason. Okay, so there's a thing called harmonics. And you'll hear that sometimes when, let's say you had two sounds going at the same time, and sometimes they get in sync and you get kind of this pulse, round, 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 that kind of thing. What's happening is that those sounds are getting in resonance, in synchronization, and they are adding to each other. Well, gravity has the same kind of effect. And so with that, you're getting a gravitational effect of Saturn on the particles that make up the rings. The rings are orbiting Saturn. Now, normally, let's say a moon collided with another moon that's orbiting Saturn, exploded into a zillion pieces. It's orbiting Saturn, and over time, the gravity of Saturn is just going to pull that stuff in. But it doesn't. And that's because there are moons at just the right position away from Saturn to be in a harmonic resonance so that the gravity of the moons are actually pulling that material back into the ring system and keeping it away from Saturn. And they're called shepherding moons because they act as shepherds. If something wants to leave a ring, either going out or in towards Saturn, those moons' gravities pull it back in. And so that's why those rings are still there and they still look so great. That's why the rings are still around. Really, there should be only a remnant of rings, but those shepherding moons keep it in sync. And if you do look at some of the images from the Cassini spacecraft, the close-ups of the rings, which I recommend because they are like space art. They are so cool. And if you look carefully at the rings, you're going to see that there are endless little ringlets, like these arcs, these lines, just repeating. But notice that they are not equally spaced. They start off like farther apart, and then they get closer, 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 closer. And that's that resonance effect that's happening with the gravity and the orbital speeds of the objects as they orbit as the planet Saturn. So that was a great question. I know I am pretty much close to the end of my time, so I guess I will give it back to Billy. Is that right?
All right, well, thank you very much, Adam. So now,
Thank you.
I'm going to switch over and coming to you from the Dark Sky Observing Site at Burton's Sugar Farm in northwestern Mississippi is Jeremy Villman with the Memphis Astronomical Society. So he's going to be giving us a look at some things outside of our solar system. Jeremy?
Thank you very much, Billy. Quick sound check. Make sure everybody can hear me all right. Cool. So once again, we're clouded out in Memphis as I speak. However, I do have some pre-recorded content from our dark sky observing site. And again, once you buy a telescope and you see the moon, you see the planets, it's kind of the next step in the progress of becoming a backyard amateur astronomer is to go after deep sky objects, and it really requires some darker skies. So unfortunately, there's a lot of light pollution in urban areas, and getting to truly dark skies takes a little bit more effort. So I'm going to show you a clip from one of our dark sky observing sessions that was taken recently. And the video quality may not be the best. As long as the audio comes in, I'll continue to play it. I'll monitor the chat. Give me the, if somebody doesn't approve of the quality, then I'll just go ahead and show you the objects that I have on video. So I'm gonna go ahead and share my screen here. So this is our dark sky site in Northwest Mississippi near Michigan City, about 45 minutes from Memphis. And we're going to try a couple things for you tonight. So this is Keith. Keith is one of our astrophotographers, and you can see he's setting his rig up. When it gets dark a little later, we're going to shoot a deep sky object using Keith's rig. So that's one of the things we're going to do. The second thing we're going to do is we're going to put a night vision eyepiece into a 10-inch Dob and look at some deep sky objects. I got my man Brian here with the night vision. I got my 10-inch Dob. We put the two together, and then we'll see what we can see. So those two things. Got a beautiful night here, Bird and Sugar Farm, looking north. Sun is setting, not a cloud in the sky. Should have good seeing conditions tonight. So we're putting the iPhone on the iPhone holder right now. And that's going to go into the eyepiece holder. And then we're going to connect the night vision.
Okay, so it's going to be sitting in the focuser like this. And of course, this is going to be sitting here.
All right.
You're going to have one dial facing you. That's in the focuser. That's the on and off button.
Dial facing me is the on and off button.
Right.
Got it.
With the on and off dial. So you turn it once to the right to turn it on.
Once to the right to turn it on.
Once to the left to turn it off.
Got it.
Got it. There's going to be one dial at the bottom right here. That's going to be gain control.
All right, so that would be my left hand. That's the gain control.
Right, that's going to be gain control, and just adjust it to
right. So when you turn it counterclockwise, or I guess to my left, there should be more gain.
Right. Yeah. It'll be quite noticeable.
Okay.
As you move it either way, it'll.
Again, this is a night vision eyepiece. So if we look at a deep sky object, we're going to see. I mean, we're going to bring a lot of detail out. It's a little bit like cheating because you're using night vision instead of a regular eyepiece. But I tell you, you really bring a lot of details out. All right, Keith is set up. What do we got, Keith?
So, William Optics 102.
William Optics 102.
Paramount MyT mount.
Paramount MyT mount.
S-Big camera.
S-Big camera. And what are we shooting tonight?
Pelican Nebula.
Pelican.
IC 5070 in Cygnus.
IC 5070 in the constellation Cygnus.
Yep.
Great target.
Thank you.
Awesome. All right, night vision and phone are connected to the 10-inch Dob. I'm turning the phone on. It's our moment of truth. Whoop, there's my towel. Both of us have face masks on, by the way. Yeah. Phone is on.
Okay, put it on just a regular camera. Just
We're going to regular camera.
First, I just want to see if it will.
See if it actually gets something here.
Yeah, first I want to see if it will focus with that. So again, I just turned it off.
Okay.
So
hang on.
So right here is the dial. Once to the right.
Okay. Once to the right.
And the gain control is right here.
On the bottom.
It's at 6 o'clock. Is at the gain controls.
6 o'clock.
And right now gain is all the way up.
Okay, turn it down.
Then now you can turn it down.
Got it.
All right, so it's showtime here. It's just before 9 o'clock. We've got the iPhone connected to the night vision in the 10-inch Dob. And we are looking at M22, the globular cluster, right off of the tip of the teapot in Sagittarius. So there you go, M22. Again, as seen on an iPhone connected to a night vision eyepiece through a 10-inch Dobsonian telescope. 10 inch is a great option as a starter scope. I paid about $350 for mine used, but even an 8-inch or a 6-inch Dobsonian would be a great starter scope. I love globulars. They're very abundant in the summer skies and they don't disappoint. They look very close in the eyepiece of a telescope to what you would see if you were to compare it to an image. They just burst into an eyepiece like a firework. Now this one's located about 10,600 light years away. It's one of the nearest globular clusters to our solar system. This is one that Harlow Shapley studied in detail a little over 100 years ago, again to determine that the solar system is not at the center of the Milky Way galaxy. So, and you can see it kind of moving here a little bit to the upper left. Again, it's not the telescope that's moving, it's actually the Earth that's moving, and then you got to keep adjusting the telescope by hand because we don't have it on a tracking mount. But that's it, M22 globular cluster in Sagittarius. All right, our next shot is M17, the Swan Nebula, otherwise known as the check mark or the Omega Nebula. And this also is just north of Sagittarius. Beautiful night. Milky Way is just bursting right now. So there we go. Again, iPhone, night vision, 10-inch Dobsonian. Here is the Omega Nebula. So this is M17, otherwise, ooh, there's a satellite going across the field of view. Cool. So this is M17, known as the Swan Nebula or the Omega Nebula. And if you look at it, it kind of looks like a swan with the body on the bottom and then the neck to the upper left. Just kind of use your imagination and you'll see a kind of a swan. So yeah, that's why they call it the Swan Nebula. Now this is an H2 region where new stars are forming. It's about 6,000 light years away from Earth. Let's go ahead and center it here in the eyepiece so you get a little bit better view of it. And this is kind of what it looks like. Now, an image of it shows a lot of bright, brilliant colors, as you can see here from this image in Wikipedia. Of course, you don't see this when you look through the eyepiece of a telescope. All you see is a gray fuzzy patch because there's not enough light coming into your telescope to stimulate the rods and the cones in your eyes where you see color. So that's why you see it as kind of a gray fuzzy patch. But this is one of the more popular summer targets. Again, this is M17, the Swan Nebula, sometimes called the Omega Nebula or the Checkmark Nebula. It's in the constellation Sagittarius, about 6,000 light years from Earth. Total solar mass is about 800 times the mass of our sun. This is, again, a stellar nursery where new stars are forming. Really great target. This is what it looks like through the eyepiece of a telescope. Very popular summer target.
Where? There we go. Yeah, just shine it on there.
I don't know, Jeremy. You might have to. Oh, there we go. Right there, Jeremy.
Yeah, that's
You got
it. That's 81 and 82.
M81 and M82. All right, two for the price of one. You're looking at two faint galaxies in the same field of view. In the upper left is M82. That's the Cigar Galaxy, about 10 o'clock in the eyepiece. And then the lower right at about 4 o'clock is Bode's Galaxy. That's M81. Now, M81 is a grand design spiral galaxy, and it really looks beautiful in an image. And here you can actually see an image that one of our astronomers, Keith Latulay, took. You'll hear from Keith in just a little bit. You get an idea of what these two galaxies look like. Now, the gravity of M81, lower right, is influencing M82, upper left. And M82 is what's called a starburst galaxy. the gravity is causing gas clouds in M82 to collapse and undergo a rapid period of star formation. So M82 is actually a very bright, luminous galaxy. And if you look at an image of it, you'll see just a lot of activity. But these are two faint fuzzies. These are what galaxies look like in the eyepiece. You don't see structure, of course. You just see kind of faint smudges. But these are separate island universes like our Milky Way, consisting of billions of stars located about 12 million light years away. Great summer target, really available any time of the year off of the bowl of the Big Dipper in Ursa Major. M81, lower right, M82, upper left. Bode's Galaxy and the Cigar Galaxy.
Yeah, we could.
You might get Whirlpool. It's kind of bright there, but
Love it.
and have you done M4 yet?
No, I haven't.
Antares. There's satellite going through M4 again.
Oh man, that's cool.
All right, I'm here with Keith. Keith is up and rolling. Gonna go ahead and just put the microphone over here so we can talk. Keith, what's going on? What we got?
All right, so we're going after Pelican Nebula, and so far here's what I did. I did the initial calibration on the mount, made sure I get the polar alignment absolutely perfect. Then I did a quick autofocus. Now remember, this is a mono camera, so the first one I'm doing is I'm doing red. So I've got it focused on that. I've got it running at a 5-minute exposure, and we've got about 94 seconds left before we come up with something. So always the first shot, you want to try to make sure everything's your target's in the right framing and everything's good with it. So the first one's kind of across your fingers to figure out what's going on. So bear with us another 72 seconds and we'll have it done. All right, we got about 12 seconds left, so bear with me just a minute. As soon as it takes a picture, we're going to see a quick flash and it'll show us exactly what it captured. So here we go. Cross your fingers. There it is. So first shot, that looks pretty good. Stars look pretty nice and round, and you can see some of the nebula there. I think this is good. I'm gonna run with this, run about 10 exposures at 5 minutes a shot, and then I'll do the green, blue, and then the alpha.
What about flats and darks?
Yeah, definitely do that, but that'll be a little bit later on. Now, one of the things I am going to have to keep track of is what my focus position is, so when I come back and do some of the flats, I can always get that right back to exactly where it is. So, I'm not quite as automated as some guys, but I have fun doing it.
All right, what do we got?
All right, so we were doing the Pelican Nebula, and we're up to 7 shots of the red filter. So just wanted to show you, a lot of times I do like to see it on the screen here, which is in SkyX, but I also like to do a real quick version in PixInsight and figure out exactly what it looks like. So I pulled up one of the exposures of the red in PixInsight, and I'm going to do a real quick screen stretch just to see what things look like. And so far, looks pretty good. Now, one of the things I do like to do is kind of magnify it a little bit and see what kind of details we can come up with. And so far, details are looking pretty good. Stars are nice and round. So far, happy with what we're seeing. A lot better. So once we finish the red, again, we'll go back and do blue, green, and hydrogen alpha. That'll be used as the kind of objective base coat to it. Kind of blends in. So that's it.
Okay, hopefully that came through all right. So I'll end with this. I know my time is about up, but I wanted to show you an image here of the Pelican Nebula that Keith is working on. You can see on the left the image that he's processing. And on the right, the actual outline. I don't know if you actually see the pelican, where the beak is, where the eye is. And then, I think with the illustration, you can kind of see what actually hopefully looks like a pelican. So this is an H2 region off of Deneb and Cygnus, again, where new stars are forming. Great astrophotography target. So astrophotography is fairly involved. I mean, the data gathering and processing can take several days, weeks, even months and years. So it's fairly involved, but that's essentially what I've got. Hopefully that came in all right. I will turn it over to Billy now if we have any questions. I think I got time for maybe one.
Yes, that was great, Jeremy. Thank you. Had one question here before we switch over. What eyepiece were you using when you were looking at the Swan Nebula?
That is a night vision eyepiece. It's a special eyepiece. Again, it's cheating because it's not true optics. You've got electronics involved that are enhancing the image. It's very, I won't get into the cost of it, but it brings out a lot of detail. I mean, it's a lot more than a telescope would cost. And I don't personally own one. That's Brian's eyepiece. But when we get together, I take my 10 or 20 inch Dob, connect it to his night vision, and that brings out a lot of detail in the deep sky objects. But this gives you an idea of what you would actually see through a standard eyepiece.
Okay, great. Thank you very much. All right, so now we're going to head up north to McGill University. So next up is Nick Vieira. He's a student studying astrophysics at the McGill Space Institute in Montreal, Canada. And tonight he'll be talking about the surprising things that we can find at the centers of some of the galaxies that we've seen tonight. So Nick, I'll turn it over to you.
Hi, everyone. Hope everyone can hear me okay. So as Billy mentioned, my name is Nick Vieira, and I'm a student at the McGill Space Institute way up in Montreal, Canada. And I'm super grateful for y'all for having me here to have an opportunity to talk about something really exciting. So I'm going to go ahead and share my screen. All right. So what I wanted to do today was take us all on a bit of a journey to the centers of some galaxies. Before I start, I want to mention that a lot of what I'm going to talk about today is the subject of research of some members of my research group and a lot of folks at McGill, and they're really the ones that make the magic happen. But without further ado, so we've seen some pretty nice galaxies tonight. We saw M81 and M82 that Jeremy just showed us. These are some really nice images from Hubble showing a lot of detail, as Jeremy was alluding to. And as Jeremy mentioned, these are sort of island universes. These are each their own galaxies like the ones that we live in, with billions of stars just like ours. They look very different is something that you'll notice right off the bat. But maybe we can find some things that they have in common. One question that we could ask is, for example, what lies at their centers? Well, I think that a good place to start would be to start close to home. So this is the image. This is the sky almost directly to the south over Nashville at 10 p.m. my time, so 9 p.m. Nashville time. And you can see Saturn and Jupiter and the moon to give you a bit of bearing. So what we're going to look for is we're going to look for the constellation Sagittarius. This one looks a little bit like a teapot, which makes it a bit easy to identify. And sort of coming out of the spout of that teapot, you can see this sort of diffuse haze cloud-like structure. And that's the actual band of the Milky Way. That's what it looks like, the Milky Way, our home galaxy, because we're actually inside it. So as I mentioned, we want to know what's at the center of these galaxies. So we're going to zoom in on that point over there that I've labeled with a marker. So this is a video that I'm going to let run. Hopefully it loads. Showing a sort of simulation, but a simulation that's built from real images taken with these world-class telescopes, showing what it would be like if we were able to zoom in faster than the speed of light, zoom in to the center of the galaxy. This is quite a long voyage. We're traveling about 25,000 light years as we go towards the center of the galaxy. And And what you can sort of have in mind as we do this is this idea of sort of being on the outskirts of town in the suburbs, and sort of looking downtown to the galactic equivalent of downtown, where there's a lot more activity, a lot more lights. And we are just coming up on the center. Here we are. And what we see is something a little mysterious. We see these stars going around some object that we can't see, or something that's flickering every now and then. So here's another image of the same thing taken by another telescope. And you can see all sorts of stars moving around something that we can't see very clearly. Here, we actually give it a name. We call it Sagittarius A star. And you can see the star, S2, going around it really quickly. This video spans about only 20 years. And so this is really, really fast for a star to move. Here you can see another video of the same thing, this time really, really cleaned up, with the paths of all of these stars around this central object highlighted, so you can make out exactly where they're going. So what you'll notice is that we can't actually see what's at the middle, but there's objects that are going around it really, really fast. Some of you might have an idea what that object at the middle could be. It's something that's really, really dark, and it's something that's really, really heavy. Because if it wasn't heavy, those stars wouldn't have to travel so fast to go around it. So let's visit the center of another galaxy and see if we can figure out what we were looking at. So our galaxy is not alone. This is one of our neighbors, M87, Messier 87. And Messier 87 is a giant galaxy, much bigger than our Milky Way. And you'll also see that it looks pretty unique. This one looks a lot more like a sphere than a disk, like the other galaxies that we saw tonight. And so, as we did with our home galaxy, let's zoom in to the center of this galaxy. So if we zoom in just a little bit, we see these beautiful structures that sort of look like plumes or jets coming from something in the middle. And now what we're going to do is we're going to zoom in on that object in the middle and figure out what that is. And surprise, what we see when we zoom all the way in is a black hole. Some of you may have seen this image. It only came out about a year ago in April of 2019. And this is the first direct image of a black hole that we've actually ever seen. In this image, what you're seeing is you're seeing light from this swirling, turbulent material going around the black hole at crazy high speeds. The dark region in the center is the actual shadow of the black hole. You might notice in this image that it's not perfectly symmetric. There's a bit of a brighter blob at the middle. And that blob is from material that's actually coming towards us, towards Earth. And so it's being beamed and it's being heated up, and we're seeing it brighter than the rest of the disk. So you can imagine in this image, the material going around this black hole clockwise. Taking this image, which was actually a huge technological feat, and required essentially building a telescope almost the size of the Earth by connecting a bunch of different telescopes. So you can see here a bunch of the different telescopes that were used. There were telescopes at the South Pole, telescopes in Hawaii, Arizona, Chile, and Spain. So this was really a huge international endeavor, an endeavor that was really decades in the making. You can see here a bunch of the institutes that were involved. What's special about this black hole is that it's not just any black hole, it's a supermassive black hole. What I mean by that is that this black hole actually weighs about 7 billion times the mass of our sun. This actually makes it one of the heaviest black holes that we know of. For scale, we can see on this image the orbit of Pluto, which is just completely dwarfed by the size of the shadow of the black hole, and also the current location of Voyager 1, a spacecraft that was launched back in the late 70s. So this thing's been zooming away from Earth for over 40 years, and it's just barely reaching, sort of the edge of the shadow of this black hole. This Voyager 1 is actually the most distant human-made object, and it's still completely dwarfed by this disk around the black hole. So from various lines of evidence, we actually think now that almost every galaxy that we see in the sky has a supermassive black hole at its center. So for example, that object that we saw in the middle of our galaxy, that mysterious flickering object, that's actually a black hole itself. This one in our center of our galaxy is not quite as big as the one in M87. It's only, which sounds silly to say, 4 million times as big as our sun. So not quite as big. And excitingly, the folks who took that beautiful image of M87 are currently working on getting an image of that black hole as well. The reason that we haven't gotten it yet is that it's proven to be quite challenging for a few reasons. First of all, because of how much it flickers, as we saw in those images, and also the fact that it's much less massive makes it so that it's a lot smaller on our telescopes. So as a parting thought, something to keep in mind the next time that you look at a galaxy, or tonight as you're thinking about the galaxies that Jeremy showed us, is that in the center of each of those galaxies, or almost all of those galaxies, there are these monsters, these monstrous black holes, gobbling up materials around them, sitting in their center, hidden from view. And with that, I will take any questions if anybody has any questions.
All right, well, thank you very much, Nick. That was excellent. There are a few questions. What is your favorite galaxy to look at with your telescope?
Ooh, that's a tough one. The whirlpool is a really, really nice one. The whirlpool, I think we were seeing it for just a bit in Jeremy's video there. One thing that I really like about the whirlpool is that that famous painting by Vincent van Gogh, Starry Night. There's some evidence that part of the inspiration for that painting was a drawing that he saw of the whirlpool in a sort of catalog of galaxies from many, many years ago. So that's a nice little fun fact that I like about the whirlpool. And it's also just absolutely gorgeous. It's hard to pick.
Yeah. What technology imaged the center of the Milky Way? Was it radio?
Yes, it's radio. You can actually see it in all sorts of wavelengths. So for example, some of the students in our research group actually look at it in the infrared. Some of the students in our group look at it in the X-ray. It really shines across the spectrum. And when you look at different parts, different kinds of light, radio or X-ray or infrared, you can look at different things that are going on. You can look at the disk, or maybe you can look at, for some black holes, those jets that we saw coming away from the black hole in M87. So the answer is radio, but yes, also all of the above.
Okay. What happens to the matter that falls into these supermassive black holes? So where does it go?
That is a very good question. If you can tell me, I think there might be a Nobel Prize in it for you. The answer is that we don't really know. Sort of the definition of a black hole is that once that matter has gone beyond the event horizon, we can never learn anything about it again. So the answer to that is I don't know. And if you can find out, please do let us all know.
And I think we've got time for one more question. So the galaxy cluster, or excuse me, the galaxy colors that we see, are those actually the colors that we're actually seeing, or are those colors basically added by the astronomers?
Yeah, so in some cases, those are colors that are added by the astronomers. So for example, I think in this image here of M82, and I would have to double check, the red area has been imaged with sort of one filter on the Hubble Space Telescope, whereas the other parts of the galaxy have been imaged by other filters on the Space Telescope. So the answer is, yeah, that there is a bit of artistic license in the way that these images are constructed, but they're constructed in a way that makes sense logically. Like this red area in M82 probably shines in a color that's very, very close to red. It's just that we can't see that color because of how far away it is.
Okay. Thank you very much. All righty. And so now coming back into the U.S., we are going to head out to Goodlettsville in northern Davidson County and visit Theo Wellington, who is a member of the Barnard Seaford Astronomical Society, and she's also a NASA JPL Solar System ambassador. I believe she's going to be showing us a star cluster tonight. So Theo, over to you.
All right. I am here. You guys hearing me?
You're a little low.
All right. Let me see if I can just go without the, is that better?
Yeah.
Okay. So you might hear crickets, but that's okay. It actually is clear here tonight, which is kind of fun. So the camera's having a fun time with the low light, but that's okay too. So I'm sitting out in my driveway, and yeah, we're going to do an open cluster tonight. And let's see if we can get the screen sharing going here. Share. All right. So hopefully, yeah, there we go. So clusters come in two basic flavors, right? Globular and open clusters. And M13 here on the left is a globular cluster. They're older, really old stars, really dense balls of several 100,000 stars. Open clusters, on the other hand, are young stars, and they're not nearly as dense. They can be a few hundred to a few thousand stars. This is M11, which is also called the wild duck cluster. And if that looks like wild ducks to you, yeah, but that's okay. Some of them look a little different to the naked eye, and so you see different things. The best known open cluster is probably the Pleiades that we see in our late fall and winter sky. But there are actually several that are easily visible to the eye, some of which you don't even think of as an open cluster, like the face of Taurus the Bull. But the Pleiades is certainly one of the best known. So in the summer sky, people tend to focus on the deep Milky Way, there around that teapot that we were seeing earlier. But we're going to flip over to the other side of the sky. Instead of looking south, we're going to look north. And the Milky Way arches all the way over the sky. It ends up here in the northern sky, going right through Cassiopeia, which looks a lot more like a W than a queen sitting in her chair. And right there is where we're going to be looking tonight at a lovely little cluster. It's actually got quite a few stars, but because it sits in the middle of the Milky Way, the effect might be a little more subtle. I'll zoom in a little bit further. So there's the end star of the W, and we're just a little bit off that. And you can see that in the neighborhood, there are a lot of other things. All these little markings here are fun deep sky objects to look at. So this is actually a lovely part of the sky to, again, just take your binoculars and just kind of cruise along it, because it's got a lot of pretty stuff to look at. All right, so we're looking at young stars, but they're not baby stars, okay? I call these millennials. The bright members of the open clusters are often red giant stars, and big stars like that are so hot that they burn through their supply of hydrogen and later helium really fast. So they're the James Deans of the universe. They live fast and they die young. The cluster we're going to look at tonight is called NGC 7789, and it's also known as Carolyn's Rose Cluster. So this is Carolyn, as in Carolyn Herschel. Let me go back. I lose my cursor on these things. There we go. See what I got next here. Yeah. And this is a Hubble Space Telescope, which is totally cheating. But you can see how the bright members here they're pretty red. So this cluster is a little bit older than the Pleiades. The big hot stars have gone red giant, so they're not big and blue and pretty anymore. All right. And that's a lovely shot of Carolyn Herschel in her older years. So looking at the telescope, that's what we're seeing right now. So this is the cluster here in the middle. And the reason it was called Carolyn's Rose Cluster is because, especially to the eye, you've got these swirls of stars, and they kind of suggest rose petals. Well, you know, you can be a little creative here. And then the denser stars in the middle. So you can make those out. Now, this cluster is about 1.7 billion years old. Our sun is more like 5 billion years old. So yeah, this is an older group of stars. They're still kind of hanging together. You know, our sun was born with a group of stars. You start with a big cloud of gas and dust, you make a pile of stars, and a lot of times over time and various interactions, the stars move apart from one another. So that today we don't really know where the other stars the sun was born with are. We've all gone our own way. But we're far enough away from this one, 8,000 light years or so, that we can still see them as a more or less compact group. So Carolyn Herschel is kind of a fun person to talk about. She's often overlooked. Her brother was better known. You might know him as the discoverer of Uranus. But they interestingly both had careers in music before they went into astronomy. John liked to compose music. Carolyn sang a lot of it with him, and they were actually had a pretty good following in England for a short time. But after they got into astronomy, she worked with her brother. You know, a lot of times if you're at a telescope and you're trying to make observations, especially back then, there was no way to record. I mean, they had no cameras, nothing like that. So you were looking visually and then making notations about what you saw. So she would sit up with her brother and keep records for him. But she got interested enough that she did a lot of work herself with a telescope. So she discovered at least 8 comets, one of which is named for her, 35P Herschel-Rigollet. It'll be back next in 2092, so wait for it. And she'd observed many others, including rediscovering Comet Encke. She also indexed Flamsteed's star catalog. It was just kind of random groupings of stars by constellations. She ended up putting them in some kind of meaningful order. She actually was granted an annual salary of £50 a year by King George, and that made her the first paid professional woman astronomer. She organized her brother's 2,500 nebulae and cluster observations, along with some of her observations, in a catalog that was first published in 1802, and later she organized them into zones by distance from the pole. So for that work, which was later named the New General Catalog, NGC, that's how new it is, right? It was published back in the 1800s. And that's what she got a gold medal from the Royal Astronomical Society for. So that was 1828. 1828, Carolyn Herschel won a gold medal. The next woman who won a gold medal from the Astronomical Society was Vera Rubin in 1996. Whew. We're making progress, but folks, it's been slow. So I'm doing 30-second exposures tonight. That's what you're seeing there. It looks like it's static, but it's not. It's refreshing every 30 seconds. And when folks do this kind of work with a camera, and this is a monochrome camera, they'll take a whole pile of pictures, and then at the end of the night, you stack them together. And that gives you a better signal ratio to your noise, allows you to pull out a little more detail. And you can stack live. It's not easy. I'm not sure if this actually looks a whole lot better, but that's currently 24 images. So we're up to about 12 minutes almost of exposure time. A lot of times the really pretty pictures you see people put up, they can be several hours worth of exposures. But you do kind of lift the stars after a while out of the background some more. All right. So that's NGC. So that's from the New General Catalog, 89. And you can see that through a small telescope, especially if you have a little bit darker sky than what I have here in Goodlettsville. It's a faint smudge to your eye. And if it were as close to us as the Pleiades are, it would be pretty spectacular. They're only like 450 or so light years off. This is 8,000. So it would be really fun if something like this, as dense as this, were as close as this. And hey, there we go. We got one of our friendly nighttime critters there. The red light doesn't seem to attract quite as many as white light would, so we're doing all right. Anyway, does anybody have any questions tonight?
Thanks, Theo. Yes, we've got a few questions here.
Okay.
So talking about how Carolyn Herschel created the index, how did she actually do the indexing or the organization of everything?
So she organized them by distance from the pole, which was kind of interesting, but that's a kind of a precursor. In the modern catalogs, everything is pretty much by right ascension, which if you're looking at a globe, you have latitude and longitude. Latitude on the sky is declination, and longitude is what we call right ascension. And the name makes almost no sense. You know, what in the world is right ascension? But the best explanation I've heard is that if you are facing north, right, everything rises on the right side of the pole. So it's ascending right. So that kind of makes sense. But it's the same sort of grid system, and that's the modern way we organize things rather than by constellations, which until somewhere in the 1900s didn't have really fixed boundaries. It would depend on the astronomer who did the catalog where he drew the lines. So it made more sense to do them by where they actually were in the sky. And she thought so too. It made life easier for her because you wanted to compare positions over time to see what was moving. So it was a whole lot easier if you could actually fix it according to, you know, at least tying it to the pole, or in our case, tying it to the coordinate system.
Okay. What telescope are you looking through right now?
So I can bounce back out of this because this isn't all that exciting. Let's see, stop sharing. There we go. So behind me here, that is a 5-inch refractor. It's a Teleview NP 127, which is a really actually nice refractor. It has a very wide field of view. It's actually, if I had, I usually put my DSLR on the back, just my regular daytime camera, and that captures a fair piece of sky then. The smaller chip in the little camera I have in there tonight just doesn't quite get as much. And it's sitting on a mount that's aligned so that one axis points at the pole, so the motor only has to turn it to keep up with the Earth's rotation. And, you know, for 30-second exposures, it can do that pretty easily.
Okay. And one other question, when's the best time to see star clusters with telescopes? So like a time of year or?
Ooh, there are great ones in almost every season. There are a whole pile of them right now, like in the deep Milky Way. There's a really beautiful one just off the tail. If you're thinking of the Scorpion as having that curving tail, and he's got that little piece at the end, that's the stinger, little 2 stars. If you take your binoculars and look there, there's 2 actually beautiful open clusters right at the end there. One is particularly easy to find. So there are actually quite a few all over the sky. And then of course we have the Pleiades in the winter. In the late spring, I like to look for, or late winter even, right in between Leo the Lion and Gemini, there is a beautiful little star cluster called the Beehive. Somebody thought it looked like a bunch of busy bees buzzing around. That's actually a naked eye object if you're out somewhere with a decently dark sky, but in Nashville, generally not. So.
Okay. Oh, really good question. Is there a good book on women astronomers through history?
Repeat that.
Is there a good book on women astronomers through history?
Ooh, I should have looked that up because actually I came across a couple while I was looking up some of this stuff. There are several. If you want to get sort of the long view about what it was like to be a woman back in the day, Galileo's Daughter is a beautiful book because it talks a lot about how they interacted, how she helped him with his work and starched his collars. And you get a good sense of how limited the opportunities were. I'm trying to think if there's a good, there probably is, and I will try to look that up so that we can maybe post it later.
Yeah. All right, well, thank you so much, Theo, that was wonderful. Okay, so not to steal the show, but back to me, everybody. So next up, if you saw the description for the event, you might have an idea of what we're going to be looking at next. I don't think I gave it away when I was doing the introduction, but we'll see. I'm going to share my screen right quick. Let me find it here. I believe it's this one. All righty. So I think everybody should be able to see my screen. You should see some stars and things on it. So the object that we're looking at is somewhere in that field of view. One of those things is not a star, at least one of those things. There might be some more things in there, we don't know. You have to do some more investigating. But to make it easier, I have positioned the telescope, which by the way, we're not looking through the big telescope that we were looking at through earlier when we were looking at the Lunar X. We're actually using the finder scope that is on the side of the main CFER telescope. It's actually somewhat similar to Theo's telescope. It's a little bit wider, it's a lot longer, but it's a refractor as well. And the reason we're using that now is because this is going to give us a much wider field. We're going to be able to see more things at once. So it can't collect as much light as the big telescope to make the fainter things brighter quicker, but it will nevertheless give us a wider field of view. So I positioned it so that we are actually looking at this little guy right here. You might have to get right up to your television screen or your computer screen, but I'll place my mouse cursor right under it. That is Pluto, believe it or not. And so you may say, well, how in the world do you know that that is Pluto? Well, if it wasn't for some really nice star charts that I found online, I would never have been able to find Pluto, probably if I tried every day for the rest of my life. But I have confirmed that this is in fact Pluto because I just took this image about 5 minutes ago. In fact, no, I take that back. The image you're seeing right now, that was actually just updated about 10 seconds ago. So I'm taking 2-minute exposures, and just like Theo's camera was updating every 30 seconds, this one, because I'm looking for something fainter, this is about 2,500 times fainter than what your eye can actually see. And because of that faintness, I need to do a little bit longer of exposure. So if I then switch over, I'm going to try to share a different window here. So bear with me 1 second. Switch over to Photoshop. All right. So what I've done here, I'm going to zoom out just a little bit here. So here's kind of the full frame. All right. And you notice that there's kind of some static over on this side. This is actually 3 different images that I've aligned. So let me go over here. I am going to turn off different layers one by one. I didn't have time to make an animation for it. So this was actually Pluto 2 nights ago. This is on August 23rd. And so I've put that line there just to kind of indicate it. And so Pluto on this, like this line is an eye. It's the dot of the eye there. I'm going to go to the image we took last night. You can see that all the stars have basically stayed in the same spot. Let me turn the previous image back on and off. You'll see how it's moving back and forth. You may see some little red things in there. These are uncalibrated images, so I haven't done any fun processing to them to make them look super nice. In fact, I got this image. This is about a 30-second exposure. I happened to get that just before the clouds rolled in that night, so I was happy with being able to get it at least. But you'll notice that if I go back and forth, we can see Pluto moving over. So this is the 23rd, it's the 24th, and then tonight's image, there's the 25th. So this looks like a or it looks like it's a pretty decent movement on the sky, but that is an incredibly small amount of movement on the sky over those past couple of nights. So, you know, this is, you know, and if we were thinking back to, you know, how big a crater appears in our telescope, that's actually a much smaller movement typically than one of those average size craters. So Pluto, it's an interesting little guy. Let me switch over to my final screen here. And we'll talk just a few moments about Pluto. Well, if I can find my presentation here, give me 1 second. Let me stop that share. All right, let me try sharing one more time. Oh, there we are. Sorry, bear with me 1 second. Let me get this back into my presentation. All right, now we're going to share. There we are. Okay, Now everybody should see a much better view of Pluto. So this is Pluto down here at the bottom right. This is Charon, its largest moon. So these are two views that are superimposed. So it's not like Charon actually orbits that close to Pluto. I'll actually show you an animation here shortly, just to give you an idea of how far it is from Pluto. But this is a nice little montage of images from the New Horizons mission that did a flyby of the Pluto system all the way back in 2015. Seems like it was just yesterday, but believe it or not, it was 5 years ago. 5 years ago, this past July, as a matter of fact. It was our first ever up-close view of Pluto and the Pluto system. So we got, before that, even the Hubble Space Telescope was basically just seeing Pluto as this tiny little ball of pixels. But the New Horizons mission, like I said, it did a flyby. It didn't actually go into orbit around these guys. It passed by them at a rate of about 10 miles per second. So it couldn't, just stop for a second and then resume on. During the hours that it was passing by the system, it was snapping images rapidly, using its onboard sensors to try to get as much data as it possibly could. And then once it left that system, then it started relaying back the information. If I'm not mistaken, that information is still coming back today. But you see that Pluto is not too much larger than its largest moon. This is a little bit difference in size from our own moon. I mentioned before how just how far away Pluto and Charon orbit from one another. This is a nice animation from the New Horizons mission as it was approaching the Pluto system. So you can see we're at about 110 million kilometers, which is about 3/4 of the distance from the Earth to the Sun. So it was still tremendously far away from this system when it took this image. But the view here, it looks like everything's kind of moving around, like maybe the spacecraft is wobbling or something. But actually the spacecraft was basically fixed on the stars so that its view wasn't changing at all. And what we're actually seeing is the movement of not only Charon orbiting around, but we're actually seeing Pluto move around as well. So it's not that Charon is doing all of the orbiting. They're both orbiting a common center of mass. In fact, that's the way gravity works. Everything is orbiting a common center of mass. So for our Earth-Moon system, the moon is about 80 times less massive than our Earth. So it does most of the orbiting, but the Earth does wobble around a little bit, okay? So that balancing point between the Earth-Moon system, it's a little below the surface of the Earth. So we are wobbling as the moon is orbiting around us. In fact, we can use this method to detect planets around other stars, even when we can't see them, because we may not be able to see the planets, but we can detect the stars wobbling, and that tells us that there's something there. So how big is Pluto compared to us? So here's our moon scaled correctly with the Earth. The distances are not scaled correctly, but if we could just set the moon, Earth, and Pluto here right next to one another, this is how big they would be. Okay, so Pluto is pretty small, and he's tremendously far away from the sun, so that makes him incredibly dim. So for those of you that are familiar with magnitudes, he's at about 15th magnitude. It's so super, super dim. So like I think I mentioned before, about 2,500 times fainter than what the human eye can detect. Pluto doesn't have just one moon, it has at least 5 moons. So some of these were discovered by the Hubble Space Telescope. In fact, I believe that 2 of them were discovered, so Styx and Kerberos were discovered as New Horizons was on its way to Pluto. So as New Horizons was getting near Pluto, the Hubble Space Telescope was trying to take images of the Pluto system to see if there were any other possible moons that it would need to try to investigate, or maybe see if there was anything that could potentially be on a collision course with it as well. But you can see that these guys down here, this is the edge of Charon. So these guys are all scaled correctly to one another, and they're scaled correctly to Charon. So these guys are incredibly tiny. You could easily walk around them in a day, probably just a few hours. Let's see. thought that there was something else that I had, but I cannot think of it off the top of my head. Oh, yes, there is. So it turns out, we're talking about small worlds here. It's a small world here on the Earth as well, because one of Dyer Observatory's first directors, Dr. Bob Hardy, he started as the director here about 1960. He was actually our second director here at Dyer Observatory. He actually attended McGill University, where Nick Vieira was broadcasting from tonight. But Dr. Hardy, he was really great at doing a science called photometry, where he's not trying to take pictures of things, but he's trying to measure exactly how bright they are. So that'll give us more information about things like sizes of objects. So one of his, it wasn't necessarily a research field for him, but it was a really big interest for him. And he really kind of considered it more of a hobby, was that he loved to study Pluto. He used the Dyer Observatory C4 telescope. I don't know if you can still see it behind me there. It's kind of hard to see in the red light here. He used this telescope to acquire data with something called a photometer, and he measured the brightness variations in Pluto. Those brightness variations were due to the fact that Pluto was rotating and that its surface wasn't uniformly bright. In fact, if we go back to this view here, here's an area that's pretty bright. So if we happen to view Pluto when this area was facing us, then it would appear just a tiny bit brighter than when this area was facing us. So he very carefully measured the brightness variations. And so he saw it get bright, dim, bright, dim, bright, dim. And by making very careful, accurate measurements, he determined from that data how long it takes Pluto to rotate. And this was done back in the 1960s. And if you actually look at his results versus today's accepted values, which data was taken from some of the most powerful telescopes on the planet and in space, he got the rotation period to within about 30 seconds of what his true rotation period is. So that's pretty phenomenal and really attests to his ability to really scrutinize data and his ability as an astronomer. So that's just a little bit of history there. I'm going to stop my screen share right quick. And I was wondering if maybe we had a few questions here. So let's see. So one of the questions is, has astronomy and computer imaging always been so closely linked? So really being able to do modern types of observational astronomy where we have computers in these very on the backs of telescopes. As cameras were being developed and computers were being developed, that was definitely being incorporated into astronomy, because before that, the best observations that we could do were with things like photographic plates, which we would then take those photographic plates, which are essentially like a big piece of film that was on glass, and develop those, and then try to very accurately measure things, essentially by hand. Okay? In fact, a lot of women astronomers were really good at doing that. Folks like Henrietta Leavitt, she, back in her day, she did not have computers to look at the spectra of stars and determine things like their temperature. But in her career, she had cataloged over 300,000 stars and became basically the world's expert on spectral classification. So nowadays, it's very rare to have especially a professional telescope where you could just go up to it and look into an eyepiece. They will have cameras on the back. There won't be an astronomer that's going up to it and looking into it and trying to draw or measure by eye how things are situated on the sky. So everything is done now electronically so that we can get the most accurate information we possibly can. And then we can take that data and show it to others. So how does Pluto get to be one of the small planets aside from the rest of our solar system? I think I'm understanding the question here. I can kind of address it two ways. So Pluto, it's so much smaller than any of the big gas giant planets like Jupiter, Saturn, Uranus, or Neptune. It's what we consider a Kuiper belt object. And this is basically a bunch of debris that is left over from our solar system's formation that did not get to become part of a larger planet. So as the solar system was forming and planets were getting into their final positions, their gravity actually influenced the orbits of a lot of these objects and ended up throwing a lot of them out into the outer solar system where Pluto is. Some of these objects got thrown into the inner solar system, one of which was likely the culprit that hit our Earth about 4 billion years ago and formed our moon. We consider it a dwarf planet today because according to the current definition of planet, a planet has to orbit the sun, it has to be big enough to form itself into a ball, and it has to have cleared its orbit. So Pluto has done the first two, but it technically hasn't done the last thing where it's cleared its orbit. There's a whole bunch of other stuff out there where it's orbiting. Okay? And that's a whole discussion for another time. We could really get into that. Do all the little moons orbit Pluto, or do some orbit Charon? As far as we know, all the moons that we have discovered are orbiting Pluto itself, and they're essentially orbiting that center of mass as well, but they are so tiny compared to Pluto that they're basically doing all the orbiting, okay? There could be a tiny little asteroid that's in orbit around Charon, but we haven't seen any of those yet. There are asteroids that we have seen out in the solar system that do have their own little moons, and not like the size of our moon. They're like tiny little asteroids. Easily you could walk around them in just a few hours. So I am out of time. I don't want to take up anybody else's time. So we are going to go to, which I believe is actually our last presenter for the evening. Last, certainly not least, maybe the best, who knows? We're going to go to John Kramer, who is here in Tennessee with the Barnard Seaford Astronomical Society. And hopefully the clouds have cleared out for him so that he can show us and talk to us a little bit about Jupiter. So John, I'll turn it over to you.
Hey, everybody. So thankful to be a part of this. Now, I'll go ahead and I'll show you real quick my all sky camera view here, because just as we were getting ready to do this, of course, this line of clouds that you'll see at the bottom of the screen are interfering right now with the view a little bit. Jupiter is that, you might be able to make it out, it's that bright star just to the lower left of that object. And of course, let's switch to our other view and let's see if we can go ahead and get any decent details here from Jupiter. So first off, Jupiter is my favorite planet because there's always things to see on Jupiter when it's visible. Even with a small pair of binoculars, you can go ahead and start to pick out what's called the 4 Galilean moons of Jupiter. Those were called Galilean moons because those were the moons that Galileo, who viewed Jupiter through a telescope for the very first time, actually was able to observe. And in our field of view right now, you're able to see 3 of the 4. So starting at the bottom, you have Callisto. No, I'm sorry, that's Ganymede at the bottom. And you have Io here, just above Jupiter. And then finally, you have Europa. Now, Callisto is kind of off the field of view, kind of far down a bit. Now, I have this overexposed so that we can see these moons specifically. So now what I'm going to do is I'm going to drop the exposure down a bit so that we can start to hopefully pick up some detail on the surface of Jupiter itself, or the cloud bands of Jupiter. So hopefully that's coming through. Now, with the variable clouds that are moving through, this is a live view. So with these clouds that are kind of moving and wisping through here, the view is going to get darker and lighter periodically. And that's the reason why is we're actually seeing or viewing through these layers of clouds of Jupiter itself. Let me center this up a bit more for us. So it's going to get a little bit fuzzier at times because of the seeing, looking through clouds is not optimal by any means. But at least we are able to pick up here 2 of the main cloud bands of Jupiter. And this is what captivated me when I first viewed Jupiter for the very first time back in 1987. I was just blown away that I could see clouds on another planet. Then on top of that, the moons, you can see moons orbiting around the other planet. And as we get in through here this evening, we'll talk a little bit more about some of those activities, et cetera, as they rotate around Jupiter itself. Now, I'll go ahead and I'll share a slide here as well, so that we can kind of identify maybe a little bit of some of the surface detail that we would be able to pick out if we had a really good view of Jupiter. Now, of course, this particular view here is taken with probably a space telescope or at least a professional observatory, but you can see all of these belts and zones of Jupiter very clearly highlighted there. Now, one of the really neat features on Jupiter that unfortunately right now is not currently visible to us is the Great Red Spot, that feature that you see over here on the lower left of the image. That is literally a storm that's been brewing on Jupiter for, well, about 300 years, they estimate at least. And yes, through a telescope with large enough aperture, clear enough skies, you'd be able to see this as well. It's a really, really neat thing to view. Now, they do call it the Great Red Spot, but it is really more of a deep orange right now. And again, Jupiter being so cool, the fifth planet from the sun, the largest planet by far, you can go ahead and actually pick up subtle changes in the Great Red Spot color. I mean, I remember back, a decade ago maybe, that the Great Red Spot itself was a lot lighter than it even appears to be right now. So that's just one of the other cool aspects. So even with a small telescope, you notice these two main belts here, the south equatorial belt and the north equatorial belt. Those two features, this belt basically here and this belt basically here, are what is actually visible. I'm going to switch back to our Jupiter view. I'm going to increase the resolution just a bit more too. Maybe that will come through a bit better. Again, we are looking through some clouds. I'm trying to optimally set the exposure here so that we can get as much detail as possible. But there you go. You can kind of start to see now we got a little bit of the main bands, and actually we've got some other belts and zones coming in too. Now, you also might notice, not quite in the middle of the view, right about here is a dark feature, and I'm betting one of that dark feature that we're seeing here is coming from, I think that might be the south equatorial belt. And that middle section here is the equatorial zone. That is a festoon. And those are dark, noticeably dark features here that you can see. And the reason that these things occur on Jupiter is because the belts and the zones, they're actually going around in different directions on Jupiter. The belts and the belts are going in one direction around the planet, and the zones are going opposite. So this creates a lot of shearing going on between the belts and the zones. And because you got that cloud and that shearing going on, you might be able to spot a lot of activity at the edge of those belts and zones. And hopefully coming through, we're picking up just a little bit of that detail as these clouds kind of pass through us again onto that. So let's go back to the other scene here. Got to pick the right one here. Always the last one, right? So you see how the festoon there is that darker feature. And again, this is not a live image, this is just a reference image, but we are picking up tonight probably something that's very you know, very close visually to that, which I just circled right here. That type of visible anomaly on Jupiter, the festoon. So all of these other cloud bands, you know, you're going to be able to pick up. You might be able to go ahead and pick up such as the north temperate belt there from time to time, this thinner belt. You might even, again, you'll pick up a lot of activity around that storm of ruin on Jupiter, which is that great red spot when that comes around into view. Let's go back to our live image. And again, what makes Jupiter really cool is that Jupiter rotates very fast. In fact, it's about just under 10 hours of rotation. So if you were to take your telescope outside, take a look at Jupiter, say it's 8 o'clock as soon as it gets dark, and come back another couple of hours later, you will noticeably see those features have rotated on the surface itself in Jupiter. You will also notice, no doubt, that the moons of Jupiter have moved in their position. And periodically, you can go ahead and catch some really, really interesting things going on with the moons, such as a shadow transit. This is when these moons that we are seeing, they're going in front of the planet, between the planet and the sun. And as they're doing that, of course, they're going to show a shadow. So a little inky black dot is going to be visible on Jupiter itself. And again, you do have to use a program that can kind of tell you when those things are going to happen. But it is just phenomenal to go ahead and catch that type of phenomenon on Jupiter for yourself visually. It's just really, really cool to do that. So it looks like we do have a little bit of steadiness. The shimmering that you're seeing, of course, is the normal atmosphere. Okay, but as the clouds kind of move through here and there, it'll get darker and probably do a little bit of shake here and there. I'm just seeing if I can tweak the focus just a little bit. I'm always messing around with focus. I never can leave well enough alone, right? But there we go. I'm gonna leave. I'm gonna leave that. So again, I'm thrilled that we're able to pick up a little bit of that detail there as well. So a couple of other cool and neat facts about Jupiter. Okay, I kind of already touched upon it. It's the 5th planet from the sun. It's the largest planet. If we were to put Earth in front of it, it would take 11 Earths to fit across it. That's how wide it is. It's actually very massive too. It's 2.5 times the mass of all the other planets combined. So it's really big out there. We're already kind of touched upon, it's got 4 large Galilean moons: Io, Ganymede, Europa, and Callisto. We've seen 3 here tonight, but it's got 67, at least that's the current count I could find, 67 other moons that are really tiny, but you know, are there nonetheless. So the Great Red Spot, that's been happening now for 300 years at least, because again, I believe Galileo spotted that first. We kind of touched upon too the rotation period. It rotates fast, relatively speaking. So you can see these details change in the span of a single night. And again, being Jupiter is so cool, another thing that happens sometimes is something impacts it. 1994, it was comet Shoemaker-Levy 9. And in 2009, an amateur astronomer discovered an impact on Jupiter. And basically, when that happens, it leaves a mark that could very well be visible to you from a backyard telescope. So a lot of cool things to view on Jupiter. It's absolutely my favorite planet. So I will leave it here, and if the admins let me know, I think I'm just about up to the time with a couple more minutes maybe for questions. So be gentle because I'm not an educator. So hey, everybody else on the line, feel free to chime in, please.
All right, thank you, John. So I guess we could start with best time to see Jupiter. Is there a certain time of year or what?
Well, you know, currently Jupiter is more of a summertime object. It's going right there about in the Milky Way. It moves kind of slow. It's hanging out in the Sagittarius constellation right now. So it's going to probably be visible for a while, well into, I would imagine, winter as well. But as you get into, well, maybe fall, maybe not necessarily winter, but as you get into springtime, it won't be visible about that time.
Okay, and is the Great Red Spot actually moving across the planet's surface, or is it stationary, or what?
Wow, that's a very, very good question. And I would have to, I don't know the answer to that myself. I know that it's literally rotating, just like you would see a hurricane on Earth over a period of time. You can, well, Hubble at least has seen that spinning motion, but I believe, and please correct me if I'm wrong, but I believe it's relatively stationary.
Yeah, it pretty much is stationary. It does very gradually move, but it's not like, you know, over the course of the week you're going to see it's moved a quarter of the way around the planet. I forget the rate that it moves, but it's really slow. So it's, yeah, basically stationary.
Yeah, great question.
Speaking of the Great Red Spot, what are the white ovals?
White ovals are just different anomalies within the cloud bands themselves. I know that they're essentially storms, and I do have a little bit of information on that. They're circular, of course. And they are usually related to the South Tropical Zone and the South Temperate Zone themselves. Again, you also have white spots that are usually actually occurred within the North or the South Equatorial belts. And there, again, I know it has to deal with the way, the convection, I believe, on Jupiter, how there is certain material being brought up. That material being brought up is cooler and it reflects more light. I think it's the methane ice. And I believe that's why it looks the color that they appear.
Okay. Let's see. Is it true that there's water in Jupiter's moon Io?
I don't know about water, but I know that Io has interesting volcanic activity going on. I think it was the Voyager telescopes that saw that material, but I don't, was it ice geysers or actually was it more of a different material? Billy, do you know that offhand?
The Voyager missions, they did image the first plumes, and it's not water, it's a lot of sulfur compounds. But yeah, those eruptions, you know, like here on the Earth, you might shoot material up a few thousand feet, you know, like rock and stuff and whatnot. But on Io, it goes up, I forget how many kilometers into the Io sky. So yeah, it's huge. I think what they may have been wondering about is Europa. Can you give us any info on that?
Oh, Europa, they think, is a great candidate for possibly harboring life, because they do expect all of those fissures and cracks that are visible from spacecraft that are flying by to be probably fractures in the ice. So they suspect that there's just a whole planet of water underneath of that thick ice material. So they definitely have that theory, but as of yet, there's no missions that I'm aware of. I think there's maybe plans, but very far off to go actually to Europa and drill down and see if they can determine any type of life within those vast water reservoirs there that they presume exist.
Yeah, and actually, speaking of water, yeah, Enceladus, one of Saturn's moons, it likely has an ocean because we've seen ice geysers coming off of that. So that might be another potentially habitable area for some sort of life. Actually, we have another question going back to Theo. Why do stars cluster?
Good question. And the two kinds of clusters are for different reasons. Globular clusters, I think that most of the theory is that those were formed very early on, and because they don't share the shape of the galaxy. So you have a galaxy like the Milky Way that's basically a big flat disk, but the globular clusters are arranged in kind of a big halo around them. So those were early stars that formed. There's so many of them, they're their own sort of mostly stable system. Gravity holds them together and they just age together. Now, over time, again, they're orbiting the center of the Milky Way, and the Milky Way's gravity will strip stars, and maybe someday they'll be gone. But they're very, very old structures that formed sort of at the, with the stars at the same time, and there's so many of them that they hold together quite well just from gravity. Open clusters form from the same cloud of gas and dust. And so something starts that cloud collapsing. You have lots of places that are a little bit denser than the rest. So you form out a whole pile of stars. And then once the gas and dust blows away, you're left with this cute little group of a couple hundred to a couple thousand stars. That's a much looser, group of stars. And so all the other stars in the galaxy around them then start to interact gravitationally. And so eventually it disrupts. But gravity pretty much shapes everything we see in the universe. It's in some ways the weakest of the four forces, but because it operates on such large scales, it's responsible for almost all the structure that we see. So it's kind of cool and fun to look at how that all works.
Here's a question I'll open up to the group. Arthur C. Clarke wrote in his novel 2010 that Jupiter gases collapse and becomes a star. Is it feasible with it being a gas giant? Anybody want to take it?
Jupiter, I'm sure, doesn't have enough mass to go ahead and start the nuclear fusion processes required to ignite the star at the core. It's large, but it's not that large.
Yeah, if memory serves, it would be, I think the smallest star is about 80 times the mass of Jupiter.
What's interesting about Jupiter, though, is there is an internal source of heat as a result of the Kelvin-Helmholtz mechanism. All the gas giants have this, I think, except for Uranus. So there is an internal source of heat as a result of the gas laws. So that's really the mechanism that started the sun before nuclear fusion kicked in. So you can think of Jupiter as a mini version of our sun before it became a star as a result of nuclear fusion. It's just that Jupiter doesn't have enough mass to go from Kelvin-Helmholtz to nuclear fusion.
Yeah, and so an analogy I'll just add on to that, if you have ever used like a one of those bicycle pumps or a pump to to pump up the tire on your car, if you let that pump run for a couple of minutes, you feel the hose, especially next to the pump itself, and it gets really hot. And that's because you have this mechanism where gas is being compressed, and that causes the gas to heat up. It's actually the basis for why air conditioners work. But Jupiter and Saturn, and yeah, I think it was Neptune, they're still collapsing slowly under gravity. I mean, they're not going at any certain speed or any specifically high speed. They're only collapsing by, it's like a few millimeters per year. But that's enough to create enough of a compression in the interior that it really heats up the interior. So Jupiter, it releases much more energy than what it actually gets from the sun. Saturn as well, and Neptune actually does it as well. Let's see, I think we've got time for one or two more questions. Are more objects coming into the solar system captured by the sun compared to Jupiter? Anybody want to take that?
I'll throw something out there. Jupiter is kind of the first safeguard of the inner solar system of objects from the outer part of the solar system. Its gravitational influence will typically either capture or alter the path of objects, which is why comets initially have a very large orbit, a very long orbit, and then it's Jupiter's gravity will affect it and shorten the orbit. But ultimately, the sun's gravitational influence reaches far beyond Jupiter's ever. Jupiter is kind of a sentry, gravitational sentry for the inner solar system.
And one final question on Jupiter. Could a boat actually float on Jupiter? It's a creative question, I have to admit. So if you tried to land on Jupiter at all, you would basically just sink down to the center. At a certain point, there probably would be a high enough fluid density where a boat, if it didn't get crushed down to something that could fit in your hand or burn up because of the incredible temperatures in the interior, there is going to be a location where eventually a boat that doesn't succumb to heat or pressure could eventually float. But that's not going to be anywhere near the surface. For instance, when the Galileo probe reached Jupiter back in the 1995, it, like Cassini, which was around Saturn, also had a probe on it that it dropped into. Instead of being on one of the moons of Jupiter, it actually dropped the probe into Jupiter so that as the probe was descending down into the atmosphere, it could start measuring things like temperatures and pressures and chemical composition, basically anything that we could think of to measure. And it didn't make it, just maybe a few % of the way down to the center of Jupiter before the heat and pressure just destroyed it. So.
I think it depends on how big the boat is too. If you had a big enough boat, maybe it would float on Jupiter. It's kind of like the question of would Saturn float in a bathtub? Depends on how big the bathtub is.
True. Yeah, that's a good way to do it, or a good way to think of it. Let's see. I'm scrolling back through to see if I've really missed any questions. Oh, Nick. This might be a good one to end with because it's a doozy of a question. So how do they connect all the telescopes all over the Earth to make that Event Horizon telescope?
Ooh, that is a doozy of a question. So the technique has a... Sorry, what was that?
Can you answer in 2 sentences or less?
Absolutely not. That's a question for the radio astronomers. It's a technique that's really decades in the making. What I will say though is that since this is such a technologically and mathematically involved technique, to make sure that they were really making an image for that black hole that made sense, they had a bunch of different teams work on it independently without talking to each other, and do a bunch of different ways of synthesizing that image, which is just good science, right? And the result from that was that they all made something that looked basically like that image that I showed you. That's my sort of cop-out for not really knowing the answer.
Oh, I'd say that's good. I will say there are some really nice videos on YouTube. If you search for Event Horizon Telescope, and it'll give you a lot of the information as to how they actually did that. They're not going to go into the super math details, but they'll give you the concepts, and it's much easier to explain it when you've got visuals there. So you did a much better explanation than I would have, Nick. So I don't see any other questions at the moment, and we are near the end of our time. So I just want to take the last couple of minutes. I do want to recognize Brian Smokler, who's with Vanderbilt University. He's the one that's been really behind the scenes this evening, making sure that our stream is going out to YouTube and make sure that everything is running smoothly tonight. I also want to thank again Helen Morissette and Alex Rockefeller, who have also been behind the scenes, and they've been monitoring the chat and handing us questions and making sure everything looked good from our end. And so our presenters, we Adam Thance from the Bays Mountain Park and Planetarium, Jeremy Veldman from the Memphis Astronomical Society, Theo Wellington and John Kramer, both from the Barnard Seaford Astronomical Society, and Theo is also a JPL Solar System Ambassador. And then last but not least, Nick Vieira from McGill University, all the way up in Canada. Thank you all so much for your time this evening and for your information. I think we had a great turnout this evening. I certainly learned a lot of stuff. So, you know, we hope to be able to do this again next month. So just be sure to check back to our website, and we'll try to give you any details we can. So thank you all for coming tonight. I certainly enjoyed myself, and I hope that you all got a lot out of it as well. So thank you again, and have a great evening.